Hello, everyone. Today I'm going to do a paper review on two papers presented by NVIDIA and MIT. So it is about the tools for evaluating deep neural network accelerator designs. The tools are called Timeloop and Accelergy. Here I show the two papers that I'm going to share today. And if you got a copy of this slide deck, you can click the link to check the paper. They also have very good tutorial and they have open source their source code on GitHub. So first of all, what is the motivation of providing these tools? So the architecture space of DNN accelerators involve two main things. First, data movement that brings data into the compute unit. And the second is arithmetic units that perform the compute. In particular, data movement is important because of the huge difference in energy costs. For instance, the cost of fetching operands from the storage element is more than 10 times than the multiply accumulate computation operations. The good news is that the number of computation is 3 orders of magnitude larger than the number of operands. In other words, we can fetch an operand once and perform a large number of arithmetic operations on it. This gives us opportunity to exploit data reuse. Consider an example of 7-dimensional network layer that we want to map to a 2D hardware array. On the algorithm side, there are several forms of reuse, namely convolutional reuse, input activation reuse, output activation reuse, and batch reuse. During mapping, we need to consider hardware reuse, which can be classified into two aspects. First, temporal reuse refers to fetching some data into a smaller storage. For example, which is the file. Then we use the value over consecutive iterations and avoid fetching data from more expensive storage, such as DRAM. Second is spatial aspect, where multiclassing means fetching data once from an expensive storage and sending it to multiple receivers. Also, forwarding means that an hardware unit use a value and then forward it to the peer units. And until here, there are several key questions arises. What are the different ways to map algorithm to hardware? How many ways of mapping are there? Turn out there are millions of alternative mappings for a single workload on a single architecture. This diagram below is a histogram showing the number of mappings on the y-axis versus energy efficiency on the x-axis. It shows that there is a 19-time differences in energy efficiency, whereas only 9 out of 480,000 mappings are within 1% optimal. Therefore, the key is to consider efficient mapping using an efficient mapper with good cost model. Note that the number of DRAM access is not enough to tell a good mapping from bad mappings. The figure on the left here shows that we need correct technology models and accurate cost model to find the optimal mapping. On the same architecture workload and mapping, as they move across technology, like here from 65 nanometer to 16 nanometer, the energy breakdown actually change. On the other hand, given the same architecture, workload, and technology, the mapping based on different technology could be suboptimal. Furthermore, Changing hardware configuration, such as adding multiple level storage, can improve energy efficiency. For instance, as shown in the diagram here, adding individual register to PE or adding partitioned register files that are carefully sized for specific data flow can improve energy efficiency. And all these kind of cases can be modeled by the two that are proposed by this paper. So the goals of this paper is to provide an approach to systematically evaluate arbitrary DNN accelerator designs. In particular, the tool should flexibly describe a wide range of architecture so that it can find optimal mapping for a wide range of workload onto the target architecture. The model needs to accurately predict energy for a wide range of accelerator designs and also handle a wide range of technologies. So there are two papers involved in this approach. If you go to the slides, there's a link to the tutorial that describes Timeloop and Accelergy. Timeloops is a tool to perform mapping exploration, and Accelergy is a tool to support time loops in providing energy estimation. So we will go deeper into the details later. So before I move on, the basic board idea is that the model part of time loops model a variety of DNN accelerator with the support of Accelergy. And the mapper's job is to find an optimal mapping to optimize data reuse. The mapper should be able to target any accelerator that the model is able to model. So why do we need Timeloop and Accelergy? According to the paper, they mentioned three major advantages. So these two are based on micro architecture model that has three properties. One is expressive, meaning that a generic hardware model covers a wide variety of accelerator. Second is fast. The evaluation speed is much faster relative to typical simulator. The last point is accurate. So as Accelergy incorporates a technology model that allows user-defined complex architectural components and plug in for various technology model. So it can accurately model different architecture and technology. So moving on to the model part of Timeloop. The model basically requires three inputs. Problems, which means the algorithm that we are trying to map, for example, DNN layers. And architecture is the hardware that we are trying to model. Mapping is the process of taking the problem, chopping it up, then distributing and scheduling the sub-problem to hardware. Here we start with a simple one-level temporal example, considering a 1D convolution. The problem description is a loop nest with an operation space in R and P dimensions. The data space consists of three tensors, input, weight, and output. Weight is projected to the R dimension, output is projected to the P dimension, and input is projected to a linear combination of R and P. So the problem just mentioned is represented by a YAML file. Then we need to describe the architecture as well. Timeloop employs a hierarchical tree-like representation as shown in the YAML file here. For instance, PE is described as a node in the subtree. Within a PE, there's a buffer implemented as SRAM with multiple entry. There's also a max unit with 8-bit words. In order to represent mapping as well, another YAML file described the data movement between the buffer and the map unit. So this example shows that at the buffer, there's a mapping of temporal type with permutation order of R equal to 3 and P equal to 16. And the permutation order is from R to P, from the inner loop to the outer loop. With the YAML description of problem, architecture, and mapping, Timeloop runs the model to output two files. One is an optimal mapping that describes tile size and the usage of the buffer space. And the second part is the statistic that describe hardware utilization, cycle counts, energy and area costs, and so forth. Moving on to the second example. So we extend it to a two-level temporal example. This example add one more node to the architecture tree, such that the system there's a system with main DRAM memory, and the PE is connected as a subtree, and this subtree is the same as the one described in the one-level example. The mapping consists of two loop nests, one for each level of the architecture hierarchy. This implies the data movement between DRAM and buffer. In the example, there are two kinds of mapping. First is the rate stationary mapping, meaning that the P's are in the buffers and R's are in the DRAM. So the inner loop goes across the output activation, but not across the weight. So the weight stays stationary within the inner loop. And the second kind of mapping is output stationary mapping. It swap the P and R loop such that R now stay in the buffer and the inner loops go through the weight and the output remains stationary. The next example is we consider adding multiple output channels to 1D convolution. In this case, the weights and output are extended to dimension k, thus an outer mode k loop is added. So to handle this case, there are two approaches. The first one is called unit untiled mapping, where we simply add the k loop on top of an output stationary mapping. In other words, the same kernel is rerun with new k at each outer iteration. The second one is k-tiling, in which the dimension k is chopped into multiple levels, like the example shown here. For instance, R equals 3 times k equals 2 tiles are allocated to the buffer. Here, the innermost loop is still output stationary, and the loop at the buffer boundary is input stationary. Such kind of tiling increase the level of input we use by putting a larger tile of weight in the buffer, and therefore reduce the input access to the main memory. And moving on to a more complicated example, This example extends the memory hierarchy to 3 levels. The new thing introduced here is level bypassing, meaning that the programmer is given the flexibility to skip data being stored at certain levels if they know exactly what to do. For instance, in this figure, the main memory stores everything. The outputs are stored in the register file, but not in the global buffer. And the weight and output are stored in the global buffer, but not in the register file. The reason of level bypassing is to avoid the energy costs of reading and writing buffer, because sometimes buffers are simply being used at FIFO and the data are not being reused. However, this is a design trade-off, as one may result in additional access to the outer buffers. So the last example here is about spatial mapping. In cases with multiple PEs are instantiated in parallel, time loops provide spatial mapping. In this example, the mapping described the partitioning of global buffer to 16 register files in 16 PEs. Hence, the K dimension is also split across 16 PEs. So if you remember the diagram before, so the model involved a tile analysis stage. So here it means tile analysis measure and records the delta of point set over space and time. What I mean here is that for each iteration of a loop, a point set move across space or time. The delta indicates that the set difference between point sets. So when in temporal case, the delta can indicate stationary and sliding window behavior and so forth. In the spatial case, delta indicates overlapping between adjacent units or describe multicasting and forwarding opportunities. The model also includes the microarchitecture model based on the outcome of tile analysis, such as tile access, multicast patterns, etc. The microarchitecture model tells us about the architecture statistics, including multiplier access, buffer access, network transfer, and so on. The model also needs to provide the energy and performance cost. So the model tells the performance from the throughput of rate limiting step across multiple multipliers, buffer, read and write ports, and networks. It also tells the energy cost via summation of cost for various activity, including access to multiplier, buffer, and networks. Then we move to the mapper side of Timeloop. So mapping, so the mapping space of choices is extremely large. Specifying the complete mapping manually can be very tedious. In realistic problems, shape and hardware topology will lead to a combinatorial explosion. As a result, the mapper needs to consider constraints to construct a reduced map space and generate mapping based on mapper parameters. So more about workspace, Mapspace. Mapper consists of a few steps. So first, it constructs a mapping template shown in the diagram here. So there are some, it's a template, and the mapper need to fill in the blanks to complete a mapping. Then the second step is to construct a map space. So it basically need to include all the ways to fill in the blanks, such as factor, permutation, and whether we do by pass or not. Since the map space is very large, we need to constrain the map space. Although it's large, but actually in reality, many accelerator is more restricted and is not able to support all mappings. Therefore, user can define map space constraint that reduce the size of map space and also prune out illegal mappings. In addition, user can specify a few more things, such as search heuristics, like linear search, random search, or a combination of both. Optimization criteria, meaning how to tell one mapping is better than the other. For example, we can look for minimizing the number of cycles, and if two mappings have the same number of cycles, then we decide which one is better by looking at the energy cost. And also the different termination condition. So if the map space is exhausted, obviously the search will stop, or the mapper reach a particular search size, so we reached the required number of weighted mappings. Or on the other hand, we can stop by timeout, meaning the loss of embedded mappings encountered. Or there can be cases we declare victory when we see no more improvement in consecutive suboptimal weighted mapping. So this is about Timeloop. And Timeloop is accompanied by Accelergy because Timeloop requires energy reference table, ERT for short, to evaluate the energy efficiency of a potential mapping. So Accelergy takes the architectural description and generate energy reference table, which we call the energy per action of each architectural component. Then Accelergy send the energy reference table to Timeloop. In this example, GLB is the global buffer as a storage unit that can be accessed, and each access consumes 100 picojoule. Traditionally, energy estimation is performed after physical layout by simulating gate level design. This leads to long simulation and turnaround time that prohibit design space exploration. However, rapid design space exploration is essential in answering many high-level questions. For example, how many levels in the memory hierarchy? How large are the memory edge level? How many PEs are there? And also the dimension of the PE array. So the goal of Accelergy is to perform fast design space exploration at the architectural stage on architectural level components. Existing accelerator estimator take architectural description with defined primitive component at basic building blocks. The energy estimator internally store an energy reference table corresponding to a specific architecture. Action count describe one-time behavior of each component, and the number usually come from a performance model such as cycle-accurate simulator. Then energy estimation is generated based on the ERT, and action count. The downside of this estimator is that if the technology change, then the corresponding ERT does not generalize to new design, and you have to rerun the whole process, which is not flexible. In order to address these issues, Accelergy support modeling of diverse architecture with various underlying technologies. Accelergy takes in architecture description in object-oriented fashion, like buffer, MAC, in SRAM type, MAC type, and so on, where each component belongs to a primitive class with associated action. So for instance, GLB belongs to SRAM class with the action of access. So instead of a fixed ERT, Accelergy incorporates an ERT or ART generator to enhance feasibility. The generator looks at the primitive component and query the plugin for energy and area numbers. After that, ART or ART are generated at runtime. The energy calculator combines ERT and action counts to generate energy estimation of each component in the design. Accelergy further improves the estimation accuracy by allowing fine-grained classification of components' one-time behavior. For instance, the energy consumption of multiplier can have a difference of 20x, depending on whether the operand are reused or gated. So reused here means the same operands, the operands stay the same in consecutive cycles, and gated multiply means some operand may be 0, so you don't need to perform calculation. Similarly, for register file can read and write from the same address, the repeated read and write, or writing the same data to different memory address, which is depicted by constant data write. So in these cases, a different energy consumption compared to random read and write. These differences lead to significant difference, and if they are not modeled, then the energy estimation would not be accurate. And in Accelergy, these properties are captured by the fine-grained components. Furthermore, Accelergy supports different open source, proprietary, or emerging technology via plugins. In practice, there are many more primitive components. For example, one could have a smart buffer, which is a storage unit with pre-programmed address generator implemented as address, and with buffer implemented as SRAM. Accelergy allows enriching simple architecture with more practical units. The drawback of allowing more complicated units is that the architecture description and action counts become more tedious and is hard to be modified. Therefore, Accelergy allowed user-defined compound component classes to represent the architecture. For example, a smart buffer class is defined as a compound component of hardware structure to capture primitive components such as address generator and buffer. Also, the read action of smart buffer is described by a combination of primitive components, which are the add of address generator and the read of buffer in this example. In summary, Accelergy take architecture description and user-defined compound component description as input, then pass this information to generate ERT. Accelergy also takes action counts which describe the runtime behavior. Based on ERT and action counts, the energy consumption is estimated more accurately. So quickly show some results presented in the paper. So there's some validation experiment show that Timeloop has 5 to 10% error on different workloads on the architecture being evaluated. Accelergy is also able to capture the fine-grained component of PE, such as zero-gated operation. Therefore, the estimation is better than previous approach like Aladdin and the others. So in conclusion, the papers present two tools. One is Timeloop, which provide a unified representation of the key architecture and implementation attributes to describe a broad space of DNN hardware accelerators. With the aid of an inaccurate speed and energy efficiency characterization, a mapper finds the best way to schedule operations and stage data on the specified architecture. The second tool, Accelergy, is an energy estimator that provides flexible energy estimation to facilitate Timeloop's energy characterization. It allows specification of arbitrary accelerator architecture designs comprised of user-defined design-specific high-level components and user-defined low-level primitive components. So this is the end of my sharing. Thank you very much for your time. And for those who attend the General Cup, you can drop the questions on the website. Thank you very much.